Welcome to 333 Analyzing Packet Fragmentation. In the previous lessons, 332, you were analyzing control messages, ICMP across and through Wireshark, and before then, you were analyzing address resolution packets, where you were asking the MAC address and the IP address. This is just another thing to analyze, or types of traffic you can analyze in Wireshark. And we'll also learn ways to kind of do suspicious activity related to this. So not this one, 333 here, packet fragmentation. What does packet fragmentation mean? Well, when we want to transmit data across the internet, we have to put them in packets. And we learned this in I think unit 2 way back in the past. So packet might have a bunch of different information. It's not just the data in there. We got to know the source address, destination address, the type of data it is, some flags in the data, all sorts of stuff in here. And you know what? That takes space. And one thing that happens in the internet when you got to send these packets, there's a limit to the size of a packet routers want to take. And I think in a way previous lesson, there was one about, ways you can do malicious activity, sending a packet that's too big, and the routers can't handle this. But, what if we want to send a big chunk of data? So, because they give an example for Ethernet traffic, which is the protocol IP address uses, the maximum transmission unit, MTU, is 1500 bytes. Well, what if you want to transfer a file that is bigger than 1500? What you're going to have to do is chunk it up into multiple packets. So the frame data can be at most 1500 bytes, only then can layer 2 place data on the physical layer wire. As with all packet activity, the operating system, specifically the packet management system, manages the fragmentation and reassembly. So basically, your computer's going to break it up into multiple packets, send it along the Ethernet cable to your other computer, and the other computer will reassemble it, put everything back together. So how do we do this? MTU size does not include the frame header or the FCS, the frame check sequence. So let's take an example of a packet. I want to send a 4,000 byte packet right here. And the IP header was 20 bytes long, and that means there's 3,980 bytes of actual data. So that's bigger than the 1,500. So what do? They're going to take the IP header and the data and break for this whole packet right here and break it up into 3 different fragments of the whole packet. So the first one, if it's 1,500 bytes max and takes 20 bytes for all that header information, they'll put 1480 in that one. And the second one, they'll put 1480. And then the remainder, 1020 bytes, they will put in the third packet. So 3 packets, breaks it up, reassembles. All right. So that's how packet fragmentation works. And there's some stuff here about how it's on different layers and all sorts of stuff, but that's the idea. Break it up, right? Well, let's see how this actually works. So we've opened up Wireshark right here, and Wireshark can go 333 and open up IP fragmentation. I'll hit the refresh button. It looks small. Oops, I logged out too. Oh, it's going to really do this to me? Oh, I have to log back into this. I'm not going to cut this out. You might as well fast forward a minute. Just going to sit here. Go back to the lesson. 333. Maybe it gets me back in right away. Just fast forward. Wait 3 minutes. Oh, good. Not going to take a long time. Excellent. Excellent. That worked quick. I like it. Let me resize this to make sure it fits in perfectly. Good. All right, we're good. So I got all the information here. And examine the first packet in here. That'd be that first one right here. In the packet list pane, observe source, destination, length, and protocol. So source, IP, destination go in here, protocol IPv4, and the length is 14 bytes. Okay. All right. In the info column, you can already see the Wireshark recognizes it as fragmented. So it says it's fragmented IP protocol. So yeah, it knows it's fragmented. In the info column, you can already see, assuming the MTU is 1500 bytes, how big is the frame header? Okay, so I guess the frame header would be 14, the remaining bytes. Do not account for any bytes for the FCS. Is that the remaining? There we go. So the frame header's 14. Okay, so yeah, there you go, 14, because the length here is 1514. I can do math. Now look at the packet details pane. That's down here. Expand the Internet Protocol part. Element in the packet records some details in here. Okay, so we're gonna. So I should probably just full screen that. Make that a little bit bigger. Can do that. Okay, so packet details here. So for packet 1, the identification is going to be X0x7474. There we go. And the flags are going to be, do I have to, flags, I'm going to go X01, and the fragment offset is 0. Let's do packet number 2. Okay, so identification is going to be OX7474, same. Okay, flags. Okay, it's going to be the same flags. I hope that's right. That seems. The fragment offset is going to be, yep, 1480. Okay, it's because, okay, so let's do the last one. I think I'm getting this now. So identification is going to be the same. So it's right there. 7474. The flags are going to be, oh, flag is different. 00. And the offset is 2960. Okay, so cool. So we have some things. Identifications are the same. Flags were the same for these two and not for this one. That was different. And then the offset. So my guess how this works, and I bet they're going to explain this later, is identification means these are all part of the same packet to be put back together. I'm guessing these two flags say, hey, there's more stuff coming. And this one says, oh, I'm done. And the offset is like where the data should start. So 0 means the beginning. And this means after the first four spot number 1480. That'd be after all this. And then 2960 would be after all that. Inspect the second and third packets, filling in the appropriate. Do the identification values for all packets match? Yes. And so we just said that. Yep. Oh, good. What's the purpose of the fragment offset? That's probably to say where the data should start. So, hey, you should be off that many spots. And is a more fragments flag set. It is set for 1 and 2, meaning more packets are coming. And for packet 3, it's not set. Okay, so let's actually look at the details there. Okay, more fragments. So that 01 represented more fragments was set. That means, hey, there should be more. But for the last one, said, no, it was not set. So, yeah. And I guess there's a don't fragment and a reserve bit. Okay. So as long as more fragments is on, it'll keep expecting more fragments of the thing. Okay. Scroll to the end of the Internet Protocol version for information. So that'd be down here. Observe the link that shows reassembled. It says observe the link that shows reassembled IPv4 in frame 3. Reassembled. Am I missing something? Oh, is this? Okay. This thing right here. All right. Observe the length column of all fragments that comprise the frame and recall how packets and frames are organized. Remember that Wireshark actually displays frames in its packet list. Okay. So the length, 1480, 1480, 548 bytes in each of those fragments. And 3 fragments at reassembled length, so put it all together is this much. And there's the data. Okay. Each displayed frame length includes a 14-byte Ethernet header. The frame header. Can you compute the size of the frame data from the entire message? Yes. It's 3508. Wait, how am I wrong? 68. Oh, okay. Note the size of the data is the size of each packet minus each packet's Ethernet header. Okay, so, but I thought it would be this. Oh, but it's missing 60 because those were like 40 byte headers, right? Okay, this is just the data, but then remember, can you compute the size of the frame data for the entire message? What might happen if the algorithm used to manage the fragmented packages is corrupted? So what happens if you, okay, I'm not going to spoiler it. What happens if the algorithm used to manage the packets is corrupted? Well, probably just the whole thing's corrupted and the packets don't open. The files are done. An error in the reconstruction the program attempting to restruct would fail could happen on a host or router, cause a problem with this networking software. So yeah, if the packet just gets put together wrong, it just fails. And I think it just depends on how the receiving computer handles that. And how does it know if it failed? How does it check that it wasn't built correctly or there was an error? And those are problems to solve. Notice the size of the data, 3,500 bytes at the end of the Internet Control Message Protocol entry. You know that the original payload is 3568 bytes. Can you guess what the extra bytes are? The header information. That was my guess. Yay. Okay. So, yeah, that's where the extra bytes are. Got it. All right. How might a large number of fragmented packets be used in an attack? So let's watch this video. So this is called a teardrop attack. So this is like all your fragments of the packets being sent over 1, 2, 3, 4, and then it rebuilds it. Yay, right? Now here's how the hacker can ruin this. What if they start putting packets in between each of those? Then you try to build this, and this is bad stuff. So a TCP teardrop attack exploits an implementation of the fragment reassembly process to crash the receiving device. It takes advantage of a weakness in the algorithm, making the device unable to detect or manage a bad fragment offset values, which results in overlapping data during assembly. So, like, you know how the data had that offset? What if I make up a packet that says, oh, put this chunk right here too in between, and you're just kind of putting some garbage stuff in between, or stuff that is malicious on purpose. This confuses the packet reassembly process and leads to the accumulation of the buggy packets like teardrops until they ultimately crash the receiving device. So if the device may not know how to handle that stuff if it's getting packets at the wrong offset. And those are these exploits. And I think what you might have learned in the last process, the last thing, it's like some routers don't know how to handle this. You think, oh, the computers handle it automatically. And that's the solution to a lot of these. But not every router knows how to handle or is set up to handle that, or is just an older router and doesn't have the features to protect against this kind of stuff. Yeah. So okay. So that's what it looks like. Let's open another one. So we're going to close this. And what does this actually look like in Wireshark? So open up the teardrop. Find the first fragmented packet in the packet list. You can scroll to do this or use the find. Fragmented packet. Let's see. Oh, that'd be number 8, right? You can scroll or just do a find, but there is the first fragmented packet right there. Okay. Is that the only fragmented packet? Okay. So it's number 8. So confirm that is fragmented. I find the identification, other fragment information in the packet details pane. So fragmented identification 0x00f2, that's coming from right here. Fragment offset is going to be 0. Flags, it's going to be x0, x1. So that means there's more stuff. And the data length in bytes is 56. Okay. Huh. Based on the length or size of the data in the packet, what do you expect the next fragment offset value to be? Okay, so if this one's 56 and starts at 0, the next offset value would be at 56 because you start at 0, so that 56 data fills 0 to 55. So the next one is 36. Oh. Oh, yeah, like the 20 bytes a header too, right? Yeah. So, yeah, that's true. Oh, wait, I was looking at time to live. Wait, no, I wasn't. To length. Okay. 36. Was that consistent? Wait, it was? Wait. Oh, because it was 1500 data. Wait. Oh, because we were looking at the fragment offset last time. Okay. That's where I'm getting confused. Okay, so this should have been 36 because the 20 bytes a header. Got it. All right. That was tricked me there. Good thing they have the hints. Next packet should be part of the same fragment stream and have the same identification value. Select the packet and confirm the fragment on the packet details pane. I'm making sure. Oh, no, okay, I'm gonna go look at spoilers here. Let's go look at teacher resources. So make sure I'm doing this right. Okay. Okay, so the next one is 9. Okay. So I'm just weirded out because it didn't say packet on here. Okay. It didn't say fragment on it. That on the info, and the last one did. So that's what kind of weirded me out right there. That's fine though. Okay, so the identification is going to be 0x00f2. 0x00f2. The fragment offset is going to be 24. The flags 0x00 and the data length. Okay. Data total length is going to be 4 because it says 24, right? What is the fragment offset? It's actually 24. Is that a problem? That should be a problem because it should have been at 36 for our offset based off the first packet. This one was at 24. So that is going to be a problem. Is that a problem? Yeah. First packet 36, second packet is supposed to be offset by only 24. The results there's an 8-byte overlap. Reassembly process can become confused when there's overlap depending on the reassembly algorithm. It can trigger a crash, rendering denial of service tag. Yeah, does it just overwrite it or just says, hey, I can't do that? What other packet details show problems? Okay. Let's see. What other things would be a problem to me? The flag, I guess, saying it's done. And the user data program, I mean, it did say there was this bad length right here. So that's kind of interesting. Let's see what it says. Oh, okay, well this is red, so that's probably bad. Oh, okay, so it flags it. The user data program entry, the length field represents a 36 ogus. Ogus? Bogus. There's supposed to be a B there. Bogus. Payload length 28. You might also be alerted to data missing or not present. Finally, the data portion represents 20 bytes. Okay. 20 bytes, but in two IPv4 fragments, we see varying sizes of 28, 36, and 4. This packet's confused. Yeah. So, yeah, there you go. There's a lot of confusion there. And the nice thing is it highlights it in red. So, perfect. Because, yeah, that'll help out. Assuming packet 9 is in fact 20 bytes long, including the IP header and data. Diagram. Did I do all that right? Assuming the packet 9 is in fact 20 bytes long. Did I say it was 20 bytes long? A fragment offset. Yeah, okay. Including the diagram. Well, you can go ahead and do this. Diagram the reassembled IP packet from the overlap, and diagram the IP packet when properly assembled. If you don't need to see that, here it is right here in the teacher guide cheat sheets. It's right here. Here's a diagram of the reassembled packet with overlap. So the idea is that you have a little bit of overlap here because you're supposed to have 36 and 20 bytes. Properly assembled, they should be back to back like this. There should be, but we got this little bit of overlap. It's a kind of a bad overlap, but I mean, the idea is that you got this bit and they're not supposed to overlap. Or, yeah, there's about 8 bytes of overlap right there. What right this time with this type of malware attack and a lack of protection measures against it, packet reassembly attempts can have a domino effect, causing the packet management system to become confused, eventually crashing the system. Yep. So let's keep going. Wireshark data visualization. This is new. Wireshark has some great data visualizations tools built into it. Graphs help you set data trends in very large capture files. For this teardrop capture, you'll use a graph to input and output. It's another way to find suspicious activity. So like this is a lot of stuff to browse through. Instead of this, what if we can get a nice graph that kind of shows it? So let's select Statistics IO Graph. Okay, so we got this thing right here. Observe this graph. The x-axis represents the time the packet was captured. So this is time right here from the start to the end. Y-axis represents the number of packets received per second. Okay, so boom, boom. Oh, that would have been neat in that last lesson with like the Smurf attack. Oh, see a bunch of boom, spiking packets. Oh well, yeah, just thinking about it right now. X-axis, y-axis number of packets per second. Notice the various spikes in the graph. They represent high packet activity. So yeah, like I was saying, that would probably been good in that last lesson. There was a lot of packets right here. Hover your cursor over the graph, and as you move your cursor, notice a small circle follows it along the graph. Circle represents a packet that is in the capture file. Select the busiest packet activity on the graph. So I'm going to select that. Oh, you can drag around? Okay, that's kind of cool. Hover your cursor. Which packet was automatically selected from the packet list? Oh, if I select one? Oh, okay. So I see it's selecting in the background. So if you select like this one, it's going to do that packet. And then what if I do this one? Okay, it does packet number 9, which is that weird one. Okay. Which packet? It's going to be packet 9. That was suspicious. How can Wireshark data visualization help you with your analysis? So yeah, like I was saying, that last one, it could have been a lot better because you could see a lot of packet activity. What? Okay, so what I don't get with this represents the number of packets received per second. So just because I receive a lot now doesn't mean it's suspicious. And I only see like one packet here. Are there multiple packets in this packet? Or maybe there's multiple things going on with that. I don't know. Okay, so well, let's keep going with this. Maybe I'll learn more. Oh no, I won't. Oh well, we're going to be using this way more. It looks fun. So protecting to and summarize this, protecting against these teardrop attacks. Well, how would a computer or router protect against this? You can prevent IP fragmentation attacks such as teardrop in a variety of ways. Most of the prevention methods stop the suspicious or malicious packets from reaching the destination. So what can you do? Malware detection methods on routers and other network devices to inspect each packet. Packet violates the fragmentation rules, it's rejected, dropped, and not sent to the destination. So if it's checks for some warnings, maybe it compares other packets and some of those flags, if it doesn't look like it makes sense, it just kind of rejects it and doesn't send it along, goes up, that's going to be a problem. You can maintain a list of untrusted sources. If a packet comes from a source known to violate rules, yeah, so if you don't trust a source, it can block certain addresses. Sure, like you can do for anything. You can inspect rate patterns of packets since it takes a malformed packets coming in all at once. Software can match this rate pattern with incoming packets and reject them. So, like they showed in that diagram, if you see a bunch of packets or maybe a bunch of activity happening at once with this guy, maybe there's a way you expect certain packets coming from a certain source at this rate, and you see too many coming in, maybe that kind of flags it. So a lot of just seeing patterns on this, and they can build a lot of automatic checks for those in software to hopefully at least limit these kind of attacks. Keeping hosts and other systems up to date with malware exploits such as these is critical. So, just a lot of this stuff is keeping your stuff up to date, making sure updates happen. And that's how you save it. All right. So do the lesson. Thanks for watching, and see you later.